We're hopping right into topic 1.4. So if you notice, the title of our topic today starts to talk about polynomial functions. Before today, we've talked about change in tandem, so that's the concavity stuff. We've talked about average rate of change. We've talked about the average rate of change on linear and quadratic functions. And now we're going to step it up a notch and we're going to do rates of change, or things that we know from rates of change about polynomial functions. This should be a big review. A lot of the vocabulary, I think there's maybe one new thing I'm going to teach you. This is something you've known before, so we should be pretty comfortable today. And I've lost my pen. Oh, it's over here. The change, yeah, so much changing. You know how it goes. So a polynomial function, you've known this. This looks kind of crazy, but it is what you think of when you think of a polynomial function. A polynomial function is any representation equivalent to this analytical form where you have a leading coefficient and some power, and then the powers get smaller each time all the way down to where there's a regular x and then a plain number by itself called a constant. And again, these are words you probably remember from Algebra 2. The leading term in a polynomial is this a sub n, and my pen died, so I'm charging it real fast. That's why my handwriting is terrible. That's an n. A sub n times x to the n. So that very first term, if it's written in standard form, is called your leading term. Does anyone remember what the degree of a polynomial would be? The highest what? Exponent. Very good. So for us, we're going to say that the degree is n because it's a part of your leading term. And then we have our leading coefficient. Does anyone remember what that is?
The coefficient with the highest degree.
Perfect. The coefficient that is attached to the x with the highest degree. So for us, we're going to call that a sub n. And again, I'm writing with my fingers, so it's going to be really ugly until my pen charges up for a second. Forgot to charge my stuff over the weekend. Great. I'm looking very professional today. I am the same. I am the same. So let's just make sure. Well, first of all, let me fix this so it looks nice now that my pen is alive. The rest of that looks okay. So let's find the leading coefficient and the degree of these different polynomials, because the leading coefficient and the degree tells us a lot of information about the polynomial that we will stick with for the next couple of lessons. So in this first polynomial for f of x, what is the leading coefficient? Okay, so leading coefficient, I just want the 3. Leading term would have been the whole thing, yes. But just the leading coefficient. I'm using LC for leading coefficient. That's fine for notes, but if you're writing it out in an answer, write the whole word out. What is the degree of this polynomial? 4. Again, I'm shortening it because it's our notes. If you're writing it in a response, you write the whole word degree. Does that make sense for us? We have our leading term, which has the leading coefficient and the degree. What if I try to trick you and I give you the equation B? What is the leading coefficient here? -7, yeah. So the question you answered here, what is the degree? Yeah, it's okay. It's Monday on a Tuesday, so we're all feeling it. But even if it's not in standard form, you're still looking. It's Tuesday, but it's the first day of the week, so it's Monday on a Tuesday. Did that only make sense to me? Okay, okay. I'm just checking. I'm just like talking over here. So the degree and the leading coefficient always comes from the leading term, which may not be in the front. It should be. We should write equations in standard form from highest to lowest degree. But if it's not, you're still looking for that biggest power. What if I ask you a challenge question like this? Ooh. This is still a polynomial. It still fits the pattern above. It is just actually more specifically a constant equation, a constant function. If I were to rewrite this, if we remember our exponent rules, I could rewrite this as 4 times x to the 0 power, because what is anything to the 0 power? 1. 4 times 1 is 1. So if I ask this again, what is the leading coefficient here? What would you say? And then what's the degree? Yeah, that just tells us it's a constant function. Constant functions, linear functions, quadratic functions, they're all technically polynomials. They're just so specific, we usually talk about them separately. Normally, we consider polynomials anything 3rd degree or higher because the rest of them have nice names. I guess cubic and quartic we give special names to as well, but you get the drift. Now, some things that are really important when it comes to polynomials is being able to identify the extrema. You know what an extrema is, you've just probably never called it that. Extrema is a general name for all of the turning points in the graph. And by turning points, the words you would have used last year, this is the maximum and minimums. But because that's like 3 words you have to say, maximum and minimum, when we're talking about them in general, we call them extrema. It's like the plural version of extremes. These are our highest and our lowest values. Okay, now we have 2 types of extrema, and we need to make sure we understand the difference between them. When I'm talking about a relative extrema, that's our first vocabulary, the word relative or local, you might see the word local there, is like any mountain or valley. Anytime the outputs change from increasing to decreasing, okay, anytime those outputs change from increasing to decreasing, meaning our slope goes from positive to negative, rate of change, slope, that is when we're going to have a relative extrema or a local extrema. So for example, like if your slope is increasing and then we start decreasing, oh look, that's a maximum. You would talk about this point up here being the maximum point, the maximum value. If we're decreasing and then all of a sudden we start increasing, we had to turn around. That's a valley. That's a minimum. So we have maximums and minimums. Those are our relative extrema. Okay. This is important because this may be just like slightly different from maybe what you would naturally think. This part right here, it says a function also has relative extrema at an endpoint. Oops, that's not a highlighter. At an endpoint on a restricted domain. So if you have arrows on the side of your graph, this totally does not matter. But if you have a restricted domain, meaning it cuts off on purpose, those endpoints are relative extrema. So if we were to just take our highlighter, I'm going to keep highlighting in orange. We have 4 points on this graph that are relative extrema. 3 of them are very obvious. The obvious ones are this one, and this one. Do we see those extrema? On the left side of this graph, what do you see at the end of the graph? An endpoint. That's a restricted domain. So that is also going to be one of the local extrema. What do you see on the right side? It's kind of small, but there is an arrow there. So there is no extrema on that side because this graph's going to keep going down for forever. So if we were to answer the question that's here, when I'm asking about local minimums and local maximums, I'm just asking for the x value where they appear. So it asks first for the local minimums. What is the x value of this local minimum? -4. That is where one of the local extrema occurs at -4. Where does the other local minimum occur? At 0. That is the x value. We're making a list. This is not a coordinate. Noted I did not put parentheses or brackets around it. It's not an interval. It's not a coordinate. It's a list of numbers. You could put the word and in between them if you wanted to. I put a comma. Okay, where are the local maximums? And where else? Fabulous. So when I'm asking about extrema, for the most part, I'm asking for their x location. Do we feel okay about that? That is relative or local extrema. But our other type of extrema is an absolute or global extrema. You'll see those words interspersed between them. It's pretty obvious from the word absolute in my mind what this is, but an absolute or a global extrema is literally just the biggest of all the big points or the smallest of all the small points. The biggest of all the big points, the smallest of all the small points. So if we were to answer the questions here, the question, if you notice, kind of changes. It asks now for a global maximum of blank at x equal to blank. So now I'm wanting to know how high or how low does this function actually go and where does that occur? So we'll answer global maximum. It's pretty obvious where it is. Okay, we have this point right here. We've identified it already as a relative maximum. This is the same graph, by the way. Nope.
It says the
Oh,
greatest of all local maxima is the absolute minimum. Is that a typo?
That is a typo. Yep. Thank you. We're going to change that word to the maximum. Nope. That's a classic me move. Hee sorry. Everything's a minimum. No. Please do when I do something silly like that. Okay. If we're looking at this, I've highlighted the highest of all the high points. Do you agree? Okay. Notice it is also a relative maximum. but it is the biggest of all the relative maximums, which means we have a global maximum of the value 2 at x equal to 3. That coordinate point is 3, 2. We have an input of 3 and an output of 2. So my global maximum, the highest it goes, is 2 at x equal to 3. Do you see the difference in those blanks? Okay, what about a global minimum? Yeah, thanks for pausing. This is the smallest of the relative minimums we had, but is it the smallest this graph will go forever? No, because we have an arrow on one side. So if we were to just like finish this graph out, like this would keep going, yeah? Does it ever get to the lowest value? No, it'd be like infinity, but we're not going to answer like that. We're going to say that it does not have a global minimum. So not all functions have the global maxes or mins. But a lot of polynomials have relatives because we have these turning points in our rates of change when our rates of change goes from increasing to decreasing and vice versa. Here's some fun facts about extrema that make a lot of sense when you start to think about them. Between two real zeros of a polynomial, there must be at least one local max or local min. Now this makes a lot of sense if I didn't write this down for you first. And we're looking at an x-axis, so let's pretend this is an x-axis, and I have a 0 here and I have a 0 here. If I'm graphing this function, and I'm coming in here, right, and I'm graphing my way and we're increasing, there's only one other way I can come back and touch that 0, and what is it doing? I'd have to like turn a corner, yeah? Which means there's a maximum in between them. What if I was doing this and I was decreasing, I hit this 0? Well, I have to go back and touch that one. What do I have to do to make that happen? I have to turn and make a minimum. So in between two zeros, there is at least one local max or local min. There may be multiple because your graph may do this. So there's multiple, but there's at least one. I did. I'm using Apple Pencil. It's just easier. Fun fact number 2. Polynomials of even degree. So quadratics, degree 2. Quartic functions, degree 4. Degree 6, degree 8. Any even degreed function must have either a global max or a global min. And it has everything to do with that leading coefficient. If you think about happy and sad parabolas, if you have a global maximum, that parabola is going to be a sad parabola, meaning your leading coefficient is going to be less than 0. You're going to have a negative number as your leading coefficient. For a global minimum, if this was a quadratic, that would be a happy parabola. That means that your leading coefficient is bigger than 0. You've got a positive number in front. So that leading coefficient back from the top actually does give us a big hint on the types of extrema we could see, especially if it's an even degreed function. Okay, so let's just practice a little bit. We're just identifying extrema pieces, right? We're just trying to make sure we get this vocabulary on the back here. I've got 3 graphs. We're going to identify the relative and absolute maxes and mins for all of these functions. I'll do the first one and I'll let you practice on the second 2. For this one, it's a classic little sad parabola. Do we have a relative minimum for this sad parabola? No, it's not available. There's none. Do we have a relative maximum? Yeah, we have one of them. How do you answer this blank, though? Just one, yeah. Okay. The place where the maximum occurs is at x equals 1.
Oh, okay. So I said 1 as the number, not 1 as how many.
Yeah, okay. I misheard you. I thought you were saying there's 1. No, it is at 1. I get it. I'm there now. Okay, if we don't have any relative minimums, there's literally no way we'll have an absolute minimum. So goodbye, that's gone too. For an absolute maximum, good morning, we're looking for the highest that it goes. How high does this go? And when does that occur? At 1. Do we see how to answer the questions? There may be more than 1. There may be 2. There may be 3 things that you're listing in each one. I want to see if we got it on the second and third graph here. For the second graph here, I'm noticing immediately that I have an endpoint, so I need to pay attention to that. I have this valley, I have this hill, and then I have an arrow on the other side, so I'm going to leave that be. That means that I have a local minimum at the x value of -2, a local maximum at the x value of -4 and 3. My global minimum does not exist. Because of the arrow going down, there's not going to be a smallest point of this graph. But there is a tallest point of this graph. The global maximum is at 2 at x equal to 3. Sweet. If we look at the other one here, I'm just going to look at the graph first to kind of see what's going on. So I'm highlighting. I've got endpoint, I've got a valley, I've got a hill, I've got a valley, I've got an endpoint. So I got to take care and make sure I know how to label all of those parts. We have a relative minimum for this graph at -3 and 3, and relative maximums at -4, at 0, and at 5. Because this is an endpoint that's bigger than the stuff around it, it is a maximum point, right? Because it's bigger than the stuff around it. An absolute minimum for this graph, our absolute minimum, the smallest it gets is -3 at x equal to -3. And the absolute max, the highest it gets is a y value of 4, which is at x equal to 5. How did we do? Good. Yeah, if the endpoints got us, that's okay. That's probably a little different than when you thought about maximums and minimums before, but those restricted domains are included as relative maxes and mins. Okay. Even though we didn't play a game at the beginning of the class, we're going to play a quick little game now on GimKit, so go ahead and try to get yourself logged in. Also, we will need our calculators after this, so if you did not pick yours up in this little transition moment, go grab your calculator. Okay, so we're using our calculators here for this next question. Okay, this would be a really like AP-styled multiple choice calculator allowed question. It says, for 0 less than or equal to t less than or equal to 3, which means from 0 to 3, the number of cars in a parking lot at time t hours can be modeled by the functions cars of t. Based on this model, at what time t does the number of cars in the parking lot change from increasing to decreasing? So if we're thinking about what this is asking us, if we're looking for something to change from increasing to decreasing, what vocabulary word from today am I looking for? A maximum. Thank you for guessing rate of change, because that's that's funny. We're looking for the maximum point, but we're going to be doing this with our calculator. Now, the important thing here is that you recognize that it has given us a very specific window to look. What are the t values or x values that it told us to look at between 0 and 3? So when we go to our calculator, kind of like the first calculator skills thing we had, we're going to go to y equals, I didn't reset my calculator, so obviously there we go. We're going to go to y equals, we're going to type in that entire function. So I'm not going to say it out loud because it's going to take me a second to type on this computer calculator. But go ahead and type all of that in, -1.37 times t, which we'll use x, because that's how the calculator thinks, raised to the 5th power, plus 4.128 x to the 4th power. I know it says t, but we're using x's. Oh no.
Is there a reason the calculator doesn't think in other variables?
It will actually by the end of this class. We are just in the XY mode setting. We will change it eventually to polar. That's in the 3rd quarter. We will be talking in R's and thetas. So it does in different settings. But if you're asking, like, why can't I use a different variable? It's just because x is so common that they just chose x to be the only thing that's on the home screen for the calculator.
Do you have chips?
Do you have 5 Quick Bucks?
Yes.
Talk to me in like 5 minutes. All right, so we've got it typed in. Sorry, it took me a minute because typing on this computer thing is weird. But before you press graph, we don't care about the entire graph. What are the x values we care about? 0 to 3. I know it says t, but remember we're talking in x's. So when I go to the window settings here, I only want to look at the x values from 0 to 3. So I'm changing my x values, my t values from 0 to 3. And because I've done this problem before and I'm going to speed up class, I also want you to change the y maximum to 50. Okay, so for your notes, just so you can be like, what did we do here? We typed the equation in and then we set the window to the following settings. We set it to 0 to 3 on the x's by negative 10 to 50. Okay. When it gives you a different range or domain that you're looking at, make sure you're only looking at that domain in the calculator. We're going to press graph. And woo, there we have our graph. We're only looking between 0 and 3, which is the only times we care about for this particular situation. What did we say we're looking for here? The maximum. Now, if I were to just point, I'd be like, yeah, the maximum's right there. Unfortunately, I need a number. There is a way to make the calculator work for you. You're going to go second trace. It's your calculate menu. We're trying to calculate something about this function. So second trace. What do you see as option 4? Maximum. Okay. Now everybody don't look down for a second. Look up at the screen. I just pressed option 4. What does it say at the bottom of the screen? Left bound. You're going to get the little flashing turtle on the left of the maximum. Is it currently on the left of this maximum? Yes. I press enter because I want to say yes. What does it switch to saying? So I'm going to click that right button for a long time until that little turtle, it looks like a turtle to me, whatever, until the little turtle goes up and over the hill and is significantly over the maximum. I'm going to press enter. What does it say now? We skipped this part. We just press enter one more time. Boom. It has zeroed in on the maximum value between the bounds that you gave it. The maximum value of this function is at x equal to 2.481. Is that right? Did I type something wrong there?
Yeah, that's what I got.
Okay, good. I must have the wrong number written on my key right here.
2.44. Yeah, in your y1, your 4 point, it's 4.2, 4.9.
Ugh. Oh no. I know, but those decimals matter in this class, so I'm going to fix it. Bow, bow. And we're going to do that again. Is this what y'all got now? Is this better? Okay, great. Thank you. So just because we want to make sure our notes are something that are worth looking at, the things that you see in your calculator, we're going to draw on our paper right here, just so we can see it. So we graphed this function, right? Give it a little sketch. It looks like this. We're finding this maximum value, and you found this value to be the coordinate point 2.4800. We'll leave it at 4 decimals. And the y value was 36.2293. Is that what y'all got? Yeah?
No.
Oh, no. What did I mess up on this time?
We have 2.4456.
Did I have another typo? I do have another typo.
Come on.
What am I doing?
It's a Tuesday on a Monday.
It's a Tuesday on a Monday. Wait, no, it's a Monday on a Tuesday. I just said yes. I'm losing it. Is that better?
This is a lot better than
2.4456?
Yes.
Phew, okay. I have arrived at the correct answer. Look. We're going to pretend like that wasn't as dramatic as I'm making it. Okay, so again, on our screen, on our notes, we write down what our calculator says so that we knew what we were doing. If you didn't remember where the maximum button was, that would be something to write down. But what we're doing to answer the actual question, it says at what time t does the number of cars in the parking lot change from increasing to decreasing? Our answer here is t equal to 2.4456. That's the time in which our slope changed from positive to negative. Our rate of change, I guess I should say, changed from positive to negative. Oh, that's what I had on my paper. Look at these typos just driving me insane. And we have answered the question. Now, before we walk away from this, you just saw how many typos I made doing this. I don't know how many you just made trying to follow along with me. I want you to reset your calculator, try this entire problem from start to finish again so you remember all the parts. You already know what you should get, but just make sure you remember the buttons. And now I'm going to walk around and actually help and not just make mistakes myself. So second plus 712, start all the way over. All All right, I know that was a little bit chaotic, but if you have any lingering questions about that process on the calculator, find me when we get into independent practice time. I think for the most part we've gotten it, or we're really close to getting it, so I'm going to keep rolling. Again, call me over later if you didn't quite get it. I got you. This last little part here is the only new piece of vocabulary that you would not have seen in Algebra 2, even though I know extrema was not the word you used in Algebra 2. But when we're talking about points of inflection are really important for us because they have everything to do with concavity and rates of changes. This is a new concept for you, but it's not hard to locate. A point of inflection, POI, point of inflection, occurs when a function changes from concave up to concave down. So maximums and minimums occurred when we went from increasing rates of change to decreasing rates of change. But points of inflections occur when we have concave up switching to concave down or vice versa. At a point of inflection, POI for short, the rate of change of a function changes from increasing to decreasing because we're changing concavity. So this is now when our rate of change is changing. I know, yeah, it's back. All of the changes. But this is something we, in this class, will only be able to eyeball. In calculus, you'll learn the exact ways to find points of inflection arithmetically, like by hand with an equation. But for us, we're just going to do it with our eyes and what we understand with concavity. So if we're looking at this graph, for example 4, it says the graph of g of x is shown on the right. Find any values of x where g has a point of inflection. I know point of inflection means concave up changing to concave down. So what I'm going to do is I'm just going to highlight this graph by its concavity. If I'm looking for the pieces that are concave up, I notice it starts being concave up until here. And this is where it's really important to know when it's switching. I can see that if I kept going, highlighting blue, my blue would be starting to curve back down, meaning that middle section is concave down. But then after that little point right there, the graph looks like a happy parabola again. So now we're back to being concave up. It is something you just have to eyeball in this class with concavity, but I find it really helpful to start to do that highlighting to make sure you know exactly when we're switching shapes. Use your hands to match up what shape it is so you know exactly when it's switching from one to the other. But what that means for us is right there when I switch colors. So at this point and at this point, those are my points of inflection. The x values where g has a point of inflection is at x equal to -1 and at x equal to 1. Those are the places where I switched highlighter colors. Those are the places that I switched from concave up to concave down and vice versa. Does that make sense? Okay, again, it's something you have to eyeball, which is kind of like nerve-wracking because you're like, what if I was off by a coordinate? We can do it. Just think about the concavity shapes. It will be decently obvious. But since we know things about rate of change, we're going to fill in these sentences here. It says, for each of the following intervals, determine if the rate of change of g is increasing or decreasing. Explain your reasoning for each answer using the features of the graph of g. Okay, this is now an interval, by the way, not coordinate points. Between the x values of 3 and 4, so I'm looking from here to here, what is happening with the average rate of change? The average rate of change is increasing. Why? Because the graph is concave up. Very good. This is also why the highlighting comes in handy. What about that next interval? That next interval is from -4 to -3. So if I'm looking at the x values of -4 and -3, I'm over here. What's happening to my graph at that point? Oh, sorry, let me rephrase. What's happening to the average rate of change at that point? It's also increasing. The average rate of change is increasing because the graph is still concave up right then. Even though it's a decreasing function at that moment, the average rate of change is increasing. It's getting less negative. Yeah. It is too vague in this class. We have to say what we're talking about. How about between -1 and 1? So on this interval from -1 to 1, what is happening to the average rate of change? Why? Ooh, what is concave down? Don't say it. The graph is concave down. Yeah. It's hard not to say that because we know what we're talking about, but it is way too vague. We have to know what we're talking about. How about between 1 and 2? The average rate of change is doing what? Increasing. Why? Thank you for saying the graph. The graph is concave up. Very good. So again, we're back to dealing with these changes in the rates of changes. When we switch from concave up to concave down, we can now call that a point of inflection. That's the vocabulary word for it. Okay.